Hello viewers, welcome to Coding Interviews channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. And I also have created several playlists to cover various categories of problems such as BFS, DFS, dynamic programming, stacks, queues, trees, linked list, graphs, and so on. Please check them out. I have uploaded the code for this problem to the GitHub repository. You can get the link from description below this video. Let's jump into today's problem. Sum root to leaf numbers. Given a binary tree containing digits from 0 to 9 only, each root to leaf path could represent a number. An example is the root to leaf path 1, 2, 3, which represents the number 1, 2, 3. So 123 basically, right? So there is a path from 1 to 2, 2 to 3, right? That will be represented as the number 123. Find the total sum of all root to leaf numbers. So that's essentially that we're asked to do. So let's go ahead and look at the example and try to understand more about the problem, right? So let's look at the example 2, right? So the binary tree has like 5 different nodes, 4 being the root node, and it has 2 children, 9 and 0, and 0 doesn't have any child nodes, but 9 has 2 more child nodes, 5 and 1, right? So if you have to look at the paths from root to leaf, right? So 4, 9, 5, that is 1, right? So basically 4, 9 and 5, so that's becomes a number, right? So 4 to 9 is the path and 9 to 5 is the path. So 4, 9, 5, I have that number written down. And the next thing is 4, 9 and 1, so that will be another number, right? 4, 9, 1 and 4, 0, that's it. So 0, there is no further, right? So what we are essentially doing is accumulating the numbers while you traverse through the tree in the further levels basically, right? So when you do the breadth first traversal, right, 4, 9 and 4, 0, 4, 9 has 2 more children, right, 5 and 1. 4, 9 will be added with 5, that becomes 4, 9, 5, and 4, 9 will be added with 1, that will become 4, 9, 1. And 4, 0, since 0 doesn't have any left or right child, it will stay as it is, 4, 0. That's how we can imagine, right? So the numbers will become 495, 491, 40. So in a given tree, right, in a given tree, the number of final numbers will be equal to the number of leaf nodes, right? So final count will be equal to number of leaf nodes, right? So if there is only 3 leaf nodes here, right, 5, 1, 0. So what is the definition of the leaf node? Leaf node is nothing but a node where it doesn't have a left subtree and right subtree, or you can say no left child and no right child, right? So then only we will call it as a leaf node, right? So the number of final numbers will be equal to the number of leaf nodes, right? And that many paths are available from root to leaf. So once you accumulate those numbers, finally you have to sum them up and return it. So that's the gist of this problem, right? So how are we going to do that, right? So that's the thing. So the simple strategy that we could take is, we start from the root node. As long as the node is not equal to null, right, we do the level down, we come and traverse the downer levels, right, and keep on accumulating the number, right, whatever. So whatever we have, right. So for example, let's go through the algorithm with this example, right. So now I have 4, that is the root node, right. So we'll have to go left and we'll have to go right, correct. So when we go left, it's 9 is there, so 4, 9, that's what we are going to accumulate, and right we will accumulate 4, 0, and but after 4, 9 again we will have to go left and go right as well, right? So, right, but for 40 we implement the similar, but anyway, left and right are null, right, because it doesn't have any left or right childs after 0, and after here if it goes left, right, that will be 5, right. So, what we are doing is 495, sorry, 495, right, and here 491, right. So, here anyway left and right are nulls, so we do not have to do anything, right. So, similarly after going through the 5, since 5 is the root, I mean leaf node, we do not have to go further. So, essentially we can just knock this off, right, since they are nulls, right. So, now these are the final numbers. So, there is a important note that we need to take here, right. So, when we go to the left subtree, we have to make sure we have to remove whatever the value that we have accumulated by going through the left subtree before going on to the right subtree, right. So, what I meant is when you go to 49 and go to left, we have accumulated 495, right. So, before going to the right subtree, we need to remove 5 here, right. So, remove 5, let me write like here, right, remove 5, right. Then only when you go to right subtree, we will get 491. Otherwise, what we are going to get, if we do not remove, we will get 4951. So, that is the number we get, which is actually wrong, right. So, for that purpose, we need to remove this. So, assuming that you are doing this process, right, in a recursive manner, right. So, whatever the numbers that you are accumulating, right, you need to make sure the accumulation happens in the right manner, right. So, let us go and look at the code to understand more, right. So, initially I have initialized the sum, the total sum to 0, and I am initializing the string builder here. So, this string builder will be used to accumulate the numbers, right. So, and I am going to traverse the entire tree, and finally whatever the sum that I accumulated, I am going to return, right. This is very simple. The majority of the logic lies in the traverse method, right. So, let us go ahead and look at the traverse method. So, first off, the base condition is if the root itself is null, right, we just return, we do not have to do any further processing. Otherwise, what we are going to do is the string builder is being passed to this method, right. So, we append the value at the root node, right, whatever the value that we have, we append at the root node. So, that means what we are essentially doing is we are appending the root node, the value is now 5. So, this will be string is equal to 4, right, that is what it is. And if at all roots left and right are null, that means you are saying it is a leaf node, right. So, if leaf, right, if so, you just get the integer out of the string representation and add it to your sum, right. Whenever you see a child node, that means you are already at the end of the path from root to leaf, you add that to the sum, right, that is what we are doing. Otherwise, so this is important, right. So, otherwise you go left and you go right also, right. So, what we are going to do is, instead of just going through left and right, we said we have to remove this 5, right, whatever we accumulated before going further for the next levels, right. So, that is what I am doing. So, here either you can use the removal or just decrement the length, so that it will be removed for you. So, 5 string builder, you can just say okay, string dot length minus minus, that will take care of removal of the 5 whatever the accumulated. So, whenever it goes to the right subtree, it will be 4 9 and 1 will be accumulated, right. So, essentially you are traversing and whatever the number that you appended, you are removing, right? So whenever you get the leaf node, you are adding that sum, right? Finally, you are going to return the sum. Let's go ahead and look at the time and space complexity for this, right? So time and space. So how much time essentially we are doing here, right? So if let's say if there are n nodes in the binary tree, right? So each node we are visiting once, right? Each node we are visiting once. We will say in that particular case the total time complexity will be order of n, right? Where n is the number of nodes in the binary tree, right? So without visiting at least once, we won't be able to achieve whatever we want, right? So what is the space complexity? So we are saying we are going to use a string builder and a sum. So sum is simple variable, so we don't really have to add much of the space for sum. But string builder is the one which we are using much of the space. But how much of the string builder we are using? So at any given time, it has only the numbers equal to the maximum height of the binary tree, right? So if there are n nodes in the binary tree, right, if they're all like let's say left skewed or a right skewed subtree, right, then in that particular case the string builder will hold all n elements, right? But if it is a well balanced tree, it will hold only the logarithmic of n, so that log n, right? So the space complexity is, the best case complexity will be log n and worst case complexity will be order of n, assuming the tree is either a left skewed or a right skewed, right? So when I say skewed, left or right skewed, that means left skewed means it only has only the left childs, right skewed means the tree has only the right childs, right? So in that particular case, right? So worst case time complexity will be order of n, right? So the time complexity is order of n and space complexity is also order of n. So if you have any further questions, please post them in the comment section below this video. I'll get back to you as soon as I can. I have posted this code to the GitHub repository. You can find the link in the description below this video. If you haven't subscribed to the channel, please go ahead and subscribe and share among your friends. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe and goodbye.